thanks. This is joint work between Thorsten Holz's group in Bochum and Ahmad Zadegi's group in Darmstadt. Actually, this should have been my second talk. Unfortunately, I wasn't able to make it in time for the VC3 cloud computing talk on Monday. Yeah, funny story. Okay, today I'm going to talk about a novel code reuse attack, and let me give you a brief introduction to code reuse attacks in general. So, code reuse attacks are are composed of two steps. First, there's the initial control flow hijacking, where the attacker exploits a buffer overflow vulnerability or a use after free condition to take control of the instruction pointer. And because today we have things like data execution prevention, attackers can rarely jump to their shellcode directly, but they need to employ a second step, which is a code reuse step. And the purpose of the code reuse step is to bypass data execution prevention mainly. And well, probably the most widely used technique here is return-oriented programming. And in the code reuse step, the attacker reuses existing pieces of code that are available in an application's address space and pieces them together such that some malicious computation is performed. For example, in ROP, the attacker injects a fake stack and then pivots the stack pointer to the stack and such that short chunks of code are chained together, ending in returns, such that some malicious computation is performed. Of course, for a code reuse attack, the attacker needs to know the locations of the code chunks he wants to reuse. So usually there's also an initial step, the information leak, where the attacker needs some vulnerability to infer the base address of executable modules in an application address space. All right, and in this talk, I'm going to concentrate on step 2, and all our contributions just concern step 2. We are presenting a novel code reuse attack. Okay, as you may know, defense against, or designing defenses against code reuse attacks is a busy field, both in academia and the industry. And I think you can roughly categorize defenses against code reuse using this table. They are first memory safety approaches, which try to prevent the initial control flow hijacking. Then there are control flow integrity approaches, which try to not to prevent the initial control flow hijacking, but rather to mitigate the following code reuse step. They try to prevent an attacker from branching to funny code locations, essentially. Then there are code shuffling and rewriting and hiding techniques, which try to make the code, to hide the code from the attacker or make it unusable for reuse. And then finally, there are heuristics-based systems which try to detect code reuse attacks at runtime using different heuristics. And last year at this conference, there was the out-of-control paper by Göktaş and others, and they essentially showed that different control flow integrity mechanisms relied on certain assumptions that are not necessarily correct in practice. And they were able to demonstrate an attack that bypassed some of these CFI systems. Additionally, there have been 4 papers last year, 2 from our groups, which showed that certain heuristics-based systems are not sufficient in practice. All right. Something's missing. And in this talk, I'm going to present counterfeit or object-oriented programming, and we essentially show that all of these defenses, or that defenses from all these categories rely on certain assumptions that aren't necessarily true in practice. Okay, the outline for the rest of this talk is as follows. I already gave the introduction. Next is a background slide on C++. Then I will present the basic idea of our code reuse attack. Then I will walk you through a simple example. I will talk about our example exploits, and there will be a discussion and a conclusion, of course. Okay, a very quick background slide on C++. In order to understand our attack, it is essential to at least have a very broad picture of what C++ objects look like in memory. So if you consider class A has 2 fields, int x and char pointer y, and an object of class A essentially looks like it is shown over there in memory. It is just composed of the fields x and y. If you now look at class B, we see class B is essentially the same as class A, but func0 is virtual. So whenever we have a virtual function in the class, objects of that class get a hidden field called the vptr. And the vptr points to a table of pointers to virtual functions. And this v table contains pointers to all virtual functions of that class. So whenever a virtual function is to be invoked at runtime, the address of this virtual function is looked up dynamically from this table. So what attackers usually do when they attack C++ applications, they hijack this vptr in order to get control over the control flow and then to mount the actual code reuse attack. And this is also what we do. And please also keep in mind that because of these v-tables, there exist pointers to all virtual functions in the C++ application, and so there are many address-taking functions in the C++ application. Okay, now the basics of our attack. The motivation for our attack was the following observation. Existing code reuse attacks, such as ROP, all exhibit one of these five characteristics. First, they branch to funny code locations. Then they use return instructions out of order. They inject or manipulate existing code pointers. They execute excessively many indirect branches, or they pivot the stack pointer. And many defenses rely on these characteristics. And in essence, it is sufficient to maintain and enforce a shadow call stack in order to fend off all ROP-based attacks. And our initial question was, do code reuse attacks necessarily exhibit these 5 characteristics? So the idea is, for our attack, if we only hijack and inject C++ vptrs, and we only reuse existing C++ virtual functions on our own injected counterfeit objects, and we call these virtual functions only from existing virtual function calling sites, then A, we don't exhibit these 5 characteristics, and B, the defender needs to be aware of C++ semantics. Now the question is, can we create a mean attack using only using whole virtual functions? And turns out we can, and here's an excerpt from our paper. We figured that we would need virtual functions of different types in order to provide the attacker with Turing-complete semantics and some extra semantics. And these are essentially all the different types you need in order to create a meaningful attack on x86, 32-bit, and 64-bit. And I'm not going to explain all of them, but I'm going to explain the main loop gadget, which is the most important one, and 2 simple ones. Okay, and we refer to these virtual functions that we use in the co-op attack as vfGadgets. So the control flow in a co-op attack looks like this. First, we have the attacker-controlled vcall, because the attacker overrode the vptr of the C++ object, and the attacker then branches to a main loop gadget. And from this main loop gadget, we invoke the actual vfGadgets that we want to execute in order to program or to have our malicious computation executed. Okay, as I said, the main loop gadget is the most important vfGadget in a co-op attack, and it's defined as follows. Let me read this for you. A virtual function that iterates over a container, for example, a C++.array or vector of object pointers, and invokes a virtual function on each object. And here's an example. It's a simple container class which has an array of object pointers, and it iterates over this array of object pointers and invokes a virtual function on each of these objects. Okay, here's an example of a main loop from Visual Studio agents.h. Just to give you an idea, it looks pretty similar to the former example. Here's an example from Chrome, and here's an example from Internet Explorer. Okay, so there are plenty of main loop gadgets available. And now, what kind of data does the attacker inject in order to mount a co-op attack? And as I said, in ROP, the attacker injects a fake stack and manipulates a vptr such that the stack pointer is pivoted to this fake stack. And in co-op, we inject a bunch of counterfeit C++ objects. We have imagine we have an object here, and we can overflow into this object. Then the attacker rewrites the VPTR of this object such that the main loop gadget is executed next, the next time a virtual function is invoked on that object. And we also inject other counterfeit objects, the counterfeit objects that correspond to the actual VF gadget that we want to execute to induce our malicious computation. Okay, this was a main loop gadget, and now comes how can you actually compute with COOP? So, as I said, we have this main loop gadget, and this main loop gadget invokes different virtual functions that we want to execute. And now I'm going to show you how we can do some meaningful computation by reusing virtual functions on our own injected counterfeit objects. Well, I'm going to present two very, very simple VF gadgets, and I'm going to show you how we can combine them. Okay, first, let's say we want to add values in our attack. We want to dynamically calculate the sum of something. So consider the class result, and the class result has at least 4 fields: value A, value B, value C, and value. And the virtual function update value adds value A, B, C, and writes the result to the field value. So if we invoke this virtual function on a counterfeit object that we injected, of which we control all the data fields, then obviously, if we invoke this virtual function on this counterfeit object, then we have a simple summation that we control, right? We have a data flow from ABC to value. Okay, so this is an example of a virtual function that we can use to do some arithmetics. And now let's say we want to write some memory. Consider the class simple string, and the virtual function set just does a string copy, right? And if we invoke the virtual function set on the counterfeit object that we injected, then we, of course, control buffer, and we can control length. So we can control the destination and the amount of data that's written. But, of course, in a meaningful code attack, you would probably want to control the destination address. You would probably want to dynamically calculate the destination address, right? So you need a data flow from one VF gadget that you execute to the next one, right? You want to dynamically calculate the address for buffer, and you want to do this using the first VF gadget I showed you, and you want then to write some data to that address that you calculated. And here's how we do this. We have the concept of overlapping counterfeit objects in COOP. So see, we have the blue object, which corresponds to the first VF gadget I showed you. This calculates the sum of ABC and writes this to the field down below. And because these counterfeit objects overlap, the next VF gadget interprets this value that we wrote as a destination pointer for this mem copy operation, string copy operation. Of course, you would also want to control the source pointer probably in a code reuse attack, but well, this is explained in the paper how you could control this. Okay, so we created different proof of concept exploits for COOP. For example, for Internet Explorer 64-bit, we created where we used existing vulnerability for step 1, and we created a COOP attack that dynamically calculated the address of the WinExec API and read the current tick count. And if the current tick count was even, then calc.exe was launched. If the current tick count was odd, then MS-paint.exe was launched. All in all, we needed to inject 21 counterfeit objects for that, of which 8 overlapped, like I showed you. And we used 8 different VF gadgets from ms.html.dll. And we also did some proof of concept exploits for Internet Explorer 32-bit and for Firefox 64-bit on Linux. And we implemented a core programming framework that relies on the Z3 theorem solver and for arranging objects in a given buffer. And we use the Metasm tool to look for useful VF gadgets in a given binary. Okay, now comes the discussion of our COOP attack. First, applicability. Of course, I mean, you can design great code reuse attacks on paper, but of course, this needs to be applicable or to be relevant. And yeah, essentially we created real-world attacks for x86, x64, and we also discussed in the paper why COOP is probably applicable to RISC architectures in general. Of course, the question is how many useful virtual functions are there usually, and we found that in reasonably sized programs, there are lots of virtual functions that you can reuse to build a cool COOP attack. Well, as I said, the main loop is probably the most essential VF gadget that we have, and it's unfortunately also the rarest one. But we discovered that main loop VF gadgets are also relatively common. For example, we found useful specimen in standard libraries of Visual Studio, which are linked to dynamically linked to very many applications on Windows. So you're likely to find all the gadgets you need in most processors on Windows. Okay, now the properties of COOP. COOP does not inject code pointers. COOP does not rely on low-level semantics of code, does not execute ROC returns or strange instruction sequences, and it does not private the stack pointer. And as such, COOP does not exhibit the aforementioned 5 code reuse characteristics, and COOP is immune against the protection of code pointers, semantics preserving, rewriting, shuffling of code, detection heuristics, existing heuristics, and generic CFI or shadow call stacks. How to prevent COOP? Well, you can protect C++ VPTRs, you can apply C++ aware control for integrity, or you can randomize C++ structures, and there's probably more you can do. The insight is that we think that in order to design a strong defense against COOP, you need to have access to source code because you need to consider high-level C++ semantics. As such, preventing COOP without access to source code is very challenging, or it's challenging. This is what we claim. And in fact, we don't know of any effective binary-only defense against COOP. So here's the table from before, and I colored some defenses that are vulnerable to COOP in red, and defenses that are not vulnerable in green. And we can see that basically all the binary, or most of the binary-only stuff is vulnerable. All right, that's it. Conclusion, I presented a novel code reuse attack that challenges common assumptions that many defenses are built on, and we make a strong argument for source code-based defenses that consider high-level programming languages semantics. Thanks.
We have time for a couple of quick questions. Can you comment on other OO languages like C#? Is there any?
We thought about that, and I think COOP could be very well applicable to Objective-C, because there's also this, well, Objective-C has even more metadata than C++, and there's even more dynamic binding going on. And we are currently looking into COOP for Objective-C, yes.
Matthias Peyer, Purdue. I love the technique, but I don't necessarily buy that you need source code semantics for that. Imagine if the gadgets will be less likely, and you will need to find gadgets in several different libraries. And even on the binary level, you can observe control flow transfers between the individual libraries if you abstract to this library granularity level. And this would be a clear indication of some COOP attack going on.
Yes,
can you comment on that?
Yes, that's true. Okay, it's true. You can probably construct something that does not require source code. And we thought about some things, especially if you monitor an application at runtime. I think it's hard to construct something that's just static.
Yeah. But if you run it, if you have some additional runtime analysis.
Yes. I think, well, our exploits for Internet Explorer, they just rely on gadgets from MS-HTML DLL. So maybe that's not too revealing. But of course, you can come up with something that's binary only. But I think our point is that then you can maybe again construct something that misuses high-level programming language features.
Yeah, we can discuss more offline.
Yes, thanks.
I was wondering if you have any more thoughts on defenses. So for instance, just to throw one out there, what if we had something like stack canaries after the VPTR, or can you suggest other defenses that you think might be effective?
I think what would be a cool defense is you could randomize object layouts, right? Or you could insert canaries. I mean, this, like a stack canary, as you say. I think there are many defenses, but the question is, can you maybe just find a simple way around that?
We can take discussion offline.
Yes.
Like, thanks here again.